Today's notes on 3.5 are about higher order derivatives. We start with some notation, starting with the second derivative. Our first derivative we call f prime, so it makes sense that our second derivative we're going to refer to as f double prime. Notice all I've done is add one more tick mark. Likewise, we could also refer to y double prime as the second derivative of y. Using function notation, we have f double prime of x, or the derivative of f prime. Using our differential notation, the second derivative looks like the following. d squared f over dx squared. Notice that in the numerator, the square is between the d and the output variable, and in the denominator, the square is after the x. We could also have third derivatives. Which would look like the triple prime. Or they could also be written with a superscript number in parentheses. Traditionally, for powers higher than 3, we use this notation. So for a fourth degree power, we would have f to the 4 in parentheses of f of x. The differential also is similar to the differential notation for the second derivative, d cubed f dx cubed. Let's take a look at how to find higher order derivatives in examples. In our first example, we're going to calculate f triple prime of -1 for a function. So let's take a look at this function. F of x equals 3x to the fifth minus 2x squared plus 7x to the negative second. To find the third derivative, we need to find each prior derivative. So we begin with the first derivative. F prime of x is equal to 15x to the fourth minus 4x, technically to the first, minus 14x to the negative third. Next, we find the second derivative. Again, using the power rule, the derivative is 60x cubed minus 4 plus 42x to the negative fourth. Last but not least, we find f triple prime, and we get 180 squared. The negative 4 goes to 0, so it goes away. And then the last term becomes negative 168x to the negative fifth. So this is our third derivative. We want f triple prime at -1. So now all we need to do is plug in -1. So 100 times -1 to the second power minus 168 times -1 to the negative fifth power. Negative power to any even power is always positive, so positive 1 times 180 is positive 180. Negative 1 to the fifth power is going to be -1, and the negative exponent just flips it to the denominator, so 1 over -1 is still -1 times the -168 that we already have gives us a positive 168. Adding these values together, we get 348. And this is our final answer. Next, we're going to find a general formula for an nth derivative. A general formula can't always be found, but in some of your homework problems, you're going to find general formulas in cases where a general formula can be found. Unfortunately, in most cases, though, the only way to find a derivative to some power, to like the 7th power, for example, would be to take the 7 derivatives. So we want to find a general derivative for the nth derivative of f of x equals x e to the x. In order to do this, we need to look for a pattern. So we just start taking derivatives. So let's find the first derivative. This is a product, so we need to use the product rule. So take a derivative, leave one alone, plus leave one alone, take a derivative. The derivative of e to the x is e to the x. So here's our derivative. I'm going to go ahead and factor out the e to the x. In factoring out the e to the x, I have e to the x times 1 plus x. So there's my first derivative. Let's find the second derivative. In using the simplified version, I'm going to also do the product rule. Take a derivative, leave one alone, plus leave the first term alone, take a derivative. And the derivative of 1 plus x is just x. So here's our second derivative, but once again, I'm going to factor out e to the x. So notice I get 1 plus x left over in the first term and a 1 in the second. 1 plus x plus 1 gives me 2 plus x. You may be seeing a pattern already. So you could think to yourself, what would I predict the third derivative to be, and see what happens. I'm going to go ahead and use the product rule once again. Take a derivative, leave it alone, plus leave it alone, take a derivative. Once again, factoring out e to the x, I see 2 plus x left over and a 1. 2 plus x plus 1 gives me 3 plus x. As you can see, we have a clear pattern here of e to the x times the nth power derivative. So in this case, the first derivative, 1. Second derivative, we have a 2. And the third derivative, we have a 3 here in this position, plus x. So I would predict that the nth derivative of this function is going to be e to the x times n plus x. The next thing we're going to cover in today's notes is acceleration. Acceleration is the derivative of velocity. Or the second derivative of position, which is why it fits in today's notes. Couple of things to note. If the slopes of the position function are increasing, the acceleration is positive. Next, if the slopes of the position function are decreasing, acceleration is negative. Last thing to note, if the slope is constant, acceleration is 0. Now let's take a look at various position graphs and talk about what the acceleration of each of them are. So let's consider a parabola that opens downward. If this is our position function, s of t, velocity is represented by the slopes of the tangent. So let's go ahead and sketch in some tangents. Here's a tangent. Here's a tangent. And here's a tangent. As you look at the tangents along this curve, the first tangent clearly has a positive slope. The second tangent that I drew in looks like it has a 0 slope, and the last tangent has a negative slope. So what's happening to the slope values as you go from left to right? They are clearly decreasing. So the slopes are decreasing, which means that the velocity is decreasing, and therefore the slopes of the velocity function would also be negative. So in this case, the acceleration is negative. So once again, if the slopes are decreasing, the acceleration is negative. All right, let's take a look at another position graph. Suppose we want to consider a parabola that opens upwards. Here's an example of a tangent line, another tangent, and yet another tangent. Here we can see a negative slope going to a slightly positive to an even more positive value. So it looks like the slopes are increasing in value. This means that our acceleration is positive. Let's consider another graph. This graph is also opening upwards. In this graph, you can see the slopes are indeed increasing. They go from very negative to slightly positive, to very positive very quickly. So here the acceleration is also positive. The reason why I'm pointing this one out is because I want you to compare it to the previous example. In both examples where the parabola opened upward, the acceleration was positive. But when comparing the acceleration of the first or the previous graph is definitely less than the acceleration of the second graph because the slopes changed more rapidly, which means the acceleration was greater. Let's take a look at one more graph. Consider a linear function. In this graph, if we were to look at the tangent lines, you would note that the tangent line would essentially be the exact same line. So therefore, the slope would be consistent all the way through. So in this case, it's positive, and it's going to be the same positive value all the way through. Since the velocity never changes, then the slope of the velocity function would then therefore be 0. And acceleration is the slope of velocity, so acceleration is 0. And that's the end of the notes.